At first it felt like a pocket had sprung a leak. A scientist reached into his coat, expecting the clean snap of a chocolate bar. Instead, his fingers closed around warm syrup smeared across the lining and soaking into the fabric. He pulled out the ruined candy and stared at it, under the hard white lights of the laboratory. The room was cold. The bar had been wrapped, kept away from any radiator or open flame, and his body heat should not have been enough to turn it into liquid. How could chocolate melt in a cold laboratory? He set the sticky bar aside and looked toward the equipment running nearby. Something invisible might have passed through the room. But before he could explain it, he needed a test. On the workbench sat a handful of dry popcorn kernels. Spencer placed them near the operating radar tube and watched. At first, nothing happened. Then one kernel jerked, split, and burst open. Another followed. Within moments, white popcorn scattered across the bench. The machine had not warmed the room. It had changed the kernels from the inside. Spencer did not treat the result as a party trick. He had spent years working with equipment that could fail without warning, and a strange reaction near a high-powered radar component was not something to dismiss. He gathered more kernels and repeated the test. Again, they sopped beside the machine while tools, walls, and his hands remained at ordinary room temperature. That narrowed the mystery. The chocolate had not melted because the entire laboratory was hot. The popcorn had not opened because a warm surface touched it. Something from the radar equipment was reaching into the food itself. For the next test, Spencer chose an egg. Its shell gave him a sealed container, and its liquid center would make any sudden change impossible to miss. He set the egg near the active tube and waited. The shell sat motionless for a few seconds. Then it cracked with a sharp snap, and the egg burst across the equipment and the nearby work surface. The result was messy, but it answered part of the question. The machine was not simply heating the air around the food. It was forcing energy into the food so rapidly that pressure built inside the egg until the shell could no longer hold it. Spencer had begun with a ruined chocolate bar. Now he was standing beside a radar component that could pop corn and detonate an egg. The accident had become a controlled experiment, and the machine was revealing a power no one had installed it to use. That hidden power had a name. The microwave effect. It happened when microwave radiation from radar's magnetron entered the candy, transferring energy into its molecules and making the chocolate heat from within. The same invisible energy could warm water, swell kernels of corn, or drive pressure through an eggshell. Spencer had not set out to invent a kitchen appliance. He was investigating what looked like an equipment malfunction. Why had the chocolate softened beside a working magnetron? Instead of dismissing the strange result, he tested it, first with popcorn, then with the egg. Those trials transformed a pocket-sized mystery into evidence that radar's heating waves could be directed and controlled. The microwave oven began not with a blueprint or a request from a hungry cook, but with a scientist asking whether a machine had failed, or accidentally revealed a second purpose. The machine at the center of this mystery had been built for a very different battlefield. During the Second World War, radar stations sent radio waves into the sky and waited for echoes from aircraft, ships, and distant objects. A pulse would leave an antenna, travel through the darkness, strike something solid, and return with clues about its distance and direction. The farther the echo, the more powerful and the original signal had to be. That demand pushed engineers toward a device called the cavity magnetron. Inside a metal vacuum tube, a heated cathode released electrons. Magnets bent those electrons into curved paths around the cathode, while carefully shaped copper cavities made them bunch together and give up energy as radio frequency waves. Each cavity acted like a tiny resonating chamber. Linked together, they could generate bursts of microwave energy far stronger than earlier equipment could produce. This was not a kitchen appliance waiting to be discovered. It was a compact radio transmitter designed to send invisible pulses toward an enemy target. The energy was meant to leave through a waveguide, travel to a radar antenna, and return as information. A radar operator saw a blip on a screen. Percy Spencer saw a melted chocolate bar. The difference was not in the waves themselves, but in where those waves ended up. When the magnetron's output was guided into a confined metal enclosure, the energy no longer passed harmlessly into open air. It bounced from the walls and crossed the food again and again. Some of that energy entered the food as an oscillating electromagnetic field. Water molecules respond strongly because each one has an uneven arrangement of electric charge. The oxygen end carries a slight negative charge, while the hydrogen end carries a slight positive charge. In a microwave field switching billions of times per second, the molecules try to turn back and forth so their charged ends follow the changing field. They cannot rotate freely. They collide with neighboring molecules, tug against one another, and lose some of that organized motion as heat. That is why a mug can come out steaming while a frozen meal still has an icy center. The energy is not making every molecule vibrate at one magical frequency. The microwave frequency used in household ovens, about 2.45 billion cycles per second, is a practical compromise. It allows energy to enter many foods while remaining manageable inside a metal cooking chamber. Water absorbs much of it, but fats, sugars, salts, and other molecules also affect how deeply the waves travel, and how efficiently energy becomes heat. Liquid water can rotate and move through the field, absorbing energy efficiently. Ice is more rigid, so it responds less readily until some of it melts. A dry cracker contains less water to absorb the waves, though its sugars and starches can still warm as moisture moves through it. Salt dissolved in water adds another pathway. Charged ions drift back and forth, producing heat as they collide with surrounding molecules. Inside the oven, the energy is also uneven. Reflected waves overlap and form regions where the field is strong and regions where it is weak, like ripples crossing on a pond. A stationary piece of food can develop a scorching edge beside a cool center. Thin portions may heat rapidly, while dense sections warm slowly. As steam forms, moisture shifts through the food, changing the way it absorbs the next wave of energy. So, a microwave could leave one bite burning and the next nearly frozen, even when both were sitting on the same plate. That strange pattern was one reason the first experiments mattered. Spencer was not simply showing that radar waves could make something warm. He was learning that the waves could be contained, redirected, and applied to a controlled object. The radar machine had detected aircraft by her interpreting echoes. Now, the same kind of energy was entering food and changing it from within. The next question was no longer whether the effect existed. It was whether engineers could make that invisible field useful without turning the machine, the room, or the meal into a hazard. The first test did not involve a recipe, a timer, or a carefully prepared laboratory sample. It involved popcorn. Spencer placed a handful of kernels near the active part of the radar equipment and switched the machine on. Within moments, the hard yellow seeds began to jump, split, and burst into white flowers of starch. Popcorn was familiar, cheap, and impossible to mistake. The machine was not merely warming the kernels from the outside. Something inside each one was changing fast enough to build pressure until the shell gave way. That result got attention, but not instant belief. Engineers, working around the radar equipment, had seen strange readings, electrical arcs, overheated components, and failed experiments. A few popped oak kernels could have been a coincidence. Perhaps the machine had warmed a nearby metal surface. Perhaps the kernels had been sitting in a hot spot. Perhaps Spencer had noticed the one successful result and ignored everything else. So he repeated it. The kernels went back into the same position. The machine ran for another short exposure. Again the shells cracked open. Again popcorn appeared in seconds. The invisible energy had produced a visible, repeatable result. Then Spencer tried something far less cooperative. An egg. He placed it near the equipment and watched its shell grow warm. From the outside nothing seemed to be happening. That was the trap. Heat was building inside the sealed shell, where expanding steam had nowhere to escape. A few moments later, the egg ruptured with a sharp pop, sending hot fragments across the work area. The result was success, but it answered a question the popcorn could not. The energy was not only making food warm, it could drive moisture inside an enclosed object into rapid expansion. The pressure had been created from within. A coworker who wanted to see the effect for himself tried the experiment again, but this time the egg sat inside a container. When the shell broke, the container caught the blast. The lesson was immediate. A food that looks harmless can become a small pressure vessel when its interior heats faster than its surface can release steam. The tests grew stranger as Spencer had searched for boundaries. Chocolate softened. Other foods warmed unevenly. Materials that seemed dry on the outside could become hot beneath the surface. Thick portions behaved differently from thin ones. A liquid could remain calm, then suddenly surge as bubbles formed throughout it. Every success exposed another problem. Food was not a uniform block, and the energy did not always distribute evenly. That made the experiments more useful, not less. Each odd result gave Spencer another variable to isolate. Where was the sample placed? How long was the equipment switched on? Was the food solid, liquid, sealed, or porous? Did the effect depend on water trapped inside it? A pocketful of melted chocolate had become a chain of practical questions, and somewhere, inside those questions, was the design of an entirely new kind of oven. The skeptical coworkers were no longer being asked to accept a strange story about a warm pocket. They could stand beside the machine, watch the kernels burst, hear the egg explode, and repeat the trial themselves. The evidence had moved from one man's observation to a sequence of demonstrations. That was the turning point. Spencer was not trying to prove that radar could make food behave strangely. He was finding out which food responded, how quickly they responded, and what could go wrong when the energy was confined inside them. Popcorn provided the clean proof. The egg supplied the warning. Together, they showed that the machine could make heat appear inside food, and that controlling that heat would be far harder than producing it. The next problem was not making the waves stronger. It was keeping them where they belonged. Inside a radar set, microwave energy was supposed to travel through a metal guide and leave through an antenna. In a cooking machine, that same energy had to stop at the food. If it escaped into the room, it could heat, expose tissue, disrupt instruments, and turn a useful device into a hazard. The solution began with the box itself. Engineers built the cooking chamber from conductive metal, usually steel, so the microwaves would bounce around inside rather than pass through the walls. The metal cavity became both oven and shield. Every seam mattered. A tiny gap around a panel could become an exit route for energy. The door created the hardest challenge. People needed to open it, place food inside, and watch what was happening. But a door also created a long crack around the chamber. Engineers overlapped its edges, added metal contact surfaces, and later placed a fine metal screen in the window. Visible light could pass through the holes. Microwaves, with their much longer wavelength, were reflected back into the cavity. That familiar dark mesh was not decoration. It was a fence made of metal. Then came the interlock. A switch connected to the door made sure the magnetron could not operate while the door was open. Not after a delay. Not when the user pressed a second button. Opening the door had to cut the high voltage circuit immediately. Many designs used more than one switch, so a single failed component would not leave the machine running. While technicians still had to check for leaks, they moved a microwave survey meter around the door, hinges, viewing window, and vents, while the oven operated with a load of water inside. The meters searched for stray energy escaping from the seams. Testing an empty oven was avoided because the waves could reflect unpredictably inside the cavity and place extra stress on the magnetron. A cup of water acted as a safe, repeatable target, absorbing much of the energy. The machine also needed limits. More power did not automatically mean better cooking. A magnetron running at high output could overheat. Food could scorch at hot spots, and sealed ingredients could build pressure until their skins burst. Timers became as important as power controls. A short burst, a pause, and another burst allowed heat to spread through the food instead of remaining concentrated at the surface or in one small pocket. This was one reason microwave cooking felt different from an ordinary oven. A conventional oven sends heat inward from hot air and metal. A microwave sends energy into the food, but the energy does not distribute itself perfectly. Water, salt, fat shape, and thickness all affect the result. Turntables, rotating antennas, and carefully shaped cavities were added to reduce cold and overheated spots. The first commercial machines were hardly kitchen appliances. The 1947 radar range stood nearly 6 feet tall, weighed hundreds of pounds, and used water cooling for its magnetron. It belonged in restaurants, ships, and institutional kitchens where the cost and size could be justified. The shielded cavity was already there. So were the door controls and safety checks. What had to shrink was everything around it. Engineers replaced bulky cooling systems, reduced the size of the high voltage supply, improved the magnetron, and made the metal chamber fit beneath a countertop. Manufacturers also had to make the controls simple enough for someone to use without understanding radar physics. Set the time. Press start. The door interlock keeps the system in a safe operating state. By the late 1960s, countertop ovens began entering American homes. Their power was far below the earliest industrial units, but The underlying bargain remained the same. Enough energy to heat food quickly, contained inside a metal chamber, released only under controlled conditions. That was the strange leap hidden inside the original accident. A melted chocolate bar had revealed a source of heat. Turning that clue into a household appliance required a shielded box, a safety system, and a way to keep invisible energy from behaving like a weapon. The machine was no longer just making food hot. It was teaching engineers how to make an invisible hazard wait behind a door. That result was more persuasive than the pocket. It could be repeated. It could be watched. And it suggested that the energy was doing something inside the food rather than simply warming its surface. Spencer kept testing, but the early experiments were not neat demonstrations. They were the kind of trials that could leave a scientist embarrassed or injured. At one point, he placed an egg near the radiation source. Pressure built inside the shell until the egg exploded, spraying hot pieces across the room. The lesson arrived as hot fragments. Spencer had found a powerful effect, not a safe cooking method. The magnetron could heat food quickly, but it could also create hot spots, burst containers, damage nearby equipment, and expose people to energy never meant to escape into the laboratory. The machine needed shielding. It needed a chamber. It needed controls, timing, and a way to keep the radiation focused where the food was. That is where the romantic version of the story leaves out the hard part. The chocolate did not invent the microwave oven. The melted bar did not explain the physics, design the metal box, or tell Spencer how much power was safe. It offered a clue, and clues are useless when nobody recognizes them. Spencer did. Then he repeated the observation, accepted the failures, and turned a dangerous radar component into a controlled experiment. His skill was not simply noticing something strange. It was refusing to treat strangeness as a coincidence until the test could answer back. The breakthrough began with an accident, but it became technology only after an engineer made the accident behave on purpose. Today, the same invisible behavior warms a meal in millions of kitchens. A hand lifts yesterday's rice from the refrigerator, slides the container onto the glass turntable, and presses 30 seconds. No flame appears. No pan heats beneath it. The food similarly grows hot from within, as the microwave's alternating field makes water-rich molecules move and collide. The appliance feels ordinary now. A box above the counter, a soft hum, a glowing timer, a plate too hot to touch. But the oven's first ingredient was not a recipe. It was a contradiction. A solid chocolate bar, a warm pocket, and a machine that had no business cooking lunch. The chocolate bar did not melt because Spencer understood the machine. Spencer understood the machine because the chocolate bar refused to melt quietly.